Morning. Today we will be going into the details of gaseous state. We have seen gaseous state as the random state of matter. There are two types of gases, ideal gases and real gases. Gases which are obeying Boyle's law, Charles' law, Avogadro's law, they are called ideal gases. We have seen in previous classes, and we had an ideal gas equation also. Isn't it? Ideal gas equation, PV is equals to nRT. We have derived from Boyle's law, Charles' law, and Avogadro's law. This is the ideal gas equation. And we have seen why gases deviate from ideal behavior. Gases deviate from ideal behavior due to their randomness. As per kinetic theory of gases, it is told that gases consist of molecules which are in motion and they move without any attraction or repulsion between them. So, if there is an attraction, that there will not be any. If there is an attraction, there will not be any ideal behavior. Now, we have seen Van der Waals equation of state, and before that, we will go into critical constants. What are critical constants? This is the today's topic, critical phenomena. When a liquid is heated in a closed vessel, some amount of liquid evaporates to form vapors. The vapor pressure of liquid increases as the temperature increases continuously. What happens here? When liquid is heated, some of the liquid converts into vapor as we go on continuing heat. What happens? Liquid continues to form vapors. A temperature will be reached where there is a clear distinction between vapor and liquid disappears. That means before that we can see the liquid state, we can see the vapor state separately, but after a certain temperature or after a certain state, the two phases merge together and that state is called critical state. So when a gas is subjected to adequate pressure at low temperature, the gas molecules come closer together and attractive forces becomes large. It becomes liquid. This is called critical phenomena. Now to explain or to understand critical phenomena, Andrews has given isotherms. And this is an important question for degree SEM1. Andrews isotherm of carbon dioxide. What are isotherms? Isotherms are graph or curves drawn. Therm means temperature. It is a relationship between pressure and volume of a gas at constant temperature. So Andrews studied the effect of pressure on volume of carbon dioxide at different temperature. He measured the volume of carbon dioxide at different pressure at constant temperature and plotted the graphs. And the graphs are known as isotherms. We can see the graphs. These are the graphs. This is the isotherm drawn at 41.8 degrees centigrade. This is the isotherm drawn at this temperature. So here we start from the lowest one, 13.1. This is the isotherm at lowest temperature. Shows that at low pressure, when pressure is very low, it will be gas. Carbon dioxide exists as gas at point A. As pressure increases, you see here pressure is increasing. From here up to here, it is liquid, totally liquid. As pressure increases, volume of gas decreases along AB. This is the AB curve. Volume decreases means it is moving towards the axis. At point B, liquefaction of gas begins here. At point B, liquefaction of gas begins and hence volume of the gas decreases. Suddenly, we are getting constant curve because volume of liquid is much less than that of a gas. The sudden decrease in volume of the gas at same pressure is indicated by a horizontal line BC. Isn't it? At point C, liquefaction of gas is complete and the increase of pressure has less effect on volume. There is very less effect of volume, so we are getting a steep curve. Hence, Steep line CD is obtained. Thus, carbon dioxide exists as a gas along AB, partially as gas and liquid along BC, and entirely liquid along CD. You have to define the first isotherm like this. Second isotherm, the temperature is 21.5, and here we can see that here this is there. You can name P, Q, or A, B, anything. This is A, B, C, D. E, F is gas. F, G is partially gas and liquid. Here liquefaction starts, and from G to H it is completely liquid. So here volume is first decreasing fast, slowly. Here volume has no change, and here there is a decrease in volume, steep change in volume. Similarly, if you go for another isotherm that is at 13.5, 31.5, now that's the point here. In the last, if you go to the last, here 31.5, you see here, the liquefaction is only at a point. Here it is along with the line. Here it is at a point. And there is no gas cannot be liquefied above this temperature. So what we conclude is above 31.5, the isotherm is continuous. This shows that above 31.1, liquefaction of gas does not take place, whatever pressure may be. Hence, the temperature above which no gas can be liquefied is known as critical temperature, and that point is called critical point. And the gas at the point is said to be in critical state. The state is called critical state, where liquefaction is not possible. The temperature, pressure corresponding to the point are called critical temperature, critical pressure, critical volume. We represent it by TC, PC, and VC. Critical constants. What are critical constants? The temperature, pressure, and volume at critical point. What is the critical point for carbon dioxide? It is 31.1. After that, gas cannot be liquefied. So this is called continuity of states or critical constants. So remember, what is critical point? The temperature or the state above which no gas can be liquefied is known as critical state. The temperature at critical point is called critical temperature. Pressure at critical point is called critical pressure, and volume similarly is called critical volume. Now, the very important thing begins here. We have to find a relation between critical constant and van der Waals constant. This will be the second question. What are critical phenomena? Draw Andrews isotherms. That is one question. Relation between critical constant and van der Waals constants. This is another point here. So we will see in the next class how this critical constants and van der Waals constants. So to understand one more point, I'll repeat. What is critical phenomena? So when a liquid is heated, I will repeat this class. When a liquid is heated, what happens? Some of the liquid form vapors, and as we go on continuously heating, the formation of vapor continues. A point will be reached where two phases, vapor phase and liquid phase, merge together. There is no distinction between liquid phase and vapor phase. This state is called critical state. So to understand this critical state in detail, Andrews plotted isotherms of carbon dioxide. What are isotherms? Iso means same, therm means temperature. The plot or the graph drawn between pressure and temperature of a gas, pressure and volume of a gas at constant temperature. The curves which explain the relationship between volume and pressure at constant temperature are called isotherms. And Andrews studied the effect of pressure and he plotted the graph. These are the graphs. You try to, this is pressure and this is volume. As we move closer, volume decreases, pressure also decreases. As we move up, pressure increasing, and we are moving away, volume increases. So at different temperature, he drew the plots. First, he has taken 13.1. He got a curve A, B, C, D. He has divided. AB is gas, BC is gas liquefaction starts here, partial liquid, partial gas. From CD, it is completely liquid. Second, he drew at 21.1 and he got EFGH. EF is gas, FG is partial liquid and gas, and GH is completely liquid. At 31.1, he got this curve, isn't it? X only is the point where liquefaction is there, otherwise there is no point. Above that, there is no liquefaction. He got this curve at 41. So this state, after this state is called critical state. And the temperature is called critical temperature. Critical temperature of carbon dioxide is 31.1. And above that, there is no liquefaction of gas. So the temperature above which gas cannot be liquefied is called critical temperature, and the pressure of the gas at a critical temperature is called critical pressure. It is denoted by PC, VC, and all these things. That is temperature. So in the next class, we will see some relationship between critical constants and van der Waals constants. So this is all for this way. Thank you. And in the next class, we will meet again.